Let's start with Newton's second law. Everything comes back to Newton's second law. It is the chewing gum on the sidewalk that is now stuck forever on our shoe. Suppose we unpack this acceleration just a little bit and talk about delta V divided by delta T. No news there. That's just kinematics. We knew that already. Sure. As long as we're just supposing different algebra, let's cross multiply. Why not? As long as we have a delta V here, we might as well write it as final minus initial. And you know what? While we're at it, let's distribute the mass.
I thought we couldn't multiply things by vectors.
Scalars, we can multiply by vectors, no problem. We call them scalars. All they do is scale
Oh,
the vector we have.
Oh,
We don't end up doing anything with the direction. Whatever the direction of delta V, multiplying by m doesn't change that. It just changes the size and the units.
okay.
Which, I mean, we had better be able to do that. Multiply the vector acceleration by the scalar mass.
Okay.
Yeah. Now, we have done something like this trick before, but you know, I don't think it's out of bounds to suggest that this looks like final thing minus initial thing. And have this mean something like that. Now, just for comparison's sake, we used to have this. Take the net force, do that for a distance, change the motion. But we just finished saying, take the net force, do that for some amount of time, change the motion. Different flavored thing. This is a vector, has a direction, it's fine. This functions exactly like the work energy theorem. Talk about the cumulative effect of applying a force and how that changes the motion. I think we are well within rights to define the product MV as a thing and to define this product as a thing, just like we define this as work and that as kinetic energy. It's baked into Newton's second law, this thing that we're saying here. It's been lurking there the whole time. I just didn't have a whole lot of cause to find it until I had written this. Accrue force over distance. All right, that lets you talk about how the motion changed according to energy. Accrue force over time. That lets you talk about how the motion changed according to whatever this is. So let's make some definitions. Let's just, make some shit up. As long as we're in this kind of thing, I'd like to call the product of net force over time. Actually, you know what? I'd like to go one step back. I'd like to call the product of force over time impulse. The symbol I'd like to use for that, obviously, is capital J.
Seriously? Is it for like jolt?
It is not for any reason that I'm aware of. We just ran out of letters.
I feel
What about
like
like Z? Yeah, Z. Or damn, because we got A. What else? Do we really use B? B as in
Base. We don't use B very much. It's kind of interesting. It makes about as much sense as J, right? Like,
Now, because J is Joule.
there's no J in this word, so, but there's no B either. So there, we might as well use the symbol B vector for all the difference it makes. Turns out we're going to use B later for magnetic field.
Of course.
What about L?
L we're going to use for angular momentum.
That was right.
Just make a new word.
Yeah.
Right.
We took the Greek one.
Well, I got to keep the Greek ones for chapter 10.
Oh my God.
Capital J. I will let convention guide my hand. The units for this are nothing special. Newton seconds.
It's called Newton seconds
It's just, well, it's because it's Newton's
per time.
time, not per. Per means divide.
Plus, no.
Times,
So,
just
times.
Newton's, just Newton seconds.
Newton seconds.
And that's what impulse is?
Yep,
Okay, so.
we have no fancy unit for it.
So could you write an example of what that unit would look like? Is it just NS or?
NS, yeah.
Okay. So like
You want to
55
know that
NS?
then? Sure.
It's, if we use the dot, then it is clear we aren't using some sort of wacky metric prefix.
So
We gotta label everything.
We do,
would just be like an S.
yes,
and
or
S.
and dot S, maybe, yeah, Newton seconds, you got it. All right. I'd also like to define this quantity. As momentum. For which, like pneumonia, I'd like to use the symbol P. This one, I know why.
Why?
At about the same time, no, that's a different P. That's with a serif and without an arrow.
Wow.
The bottom's called a serif?
Serif. SERIF.
that needs to
When,
be
you know
worded.
how, when you, in Word, when you look at certain fonts, some of them say sans serif.
Oh.
It means they don't have the little feet on the capital letters.
So you need that for power?
On the board, when I want to write power, I'll put the little foot on the bottom of the P so we know it's a capital. This doesn't have one. So we know that it's lowercase and it's got the arrowhead on it. So we know that it is not power because power is scalar.
So why is it P?
Because at about the same time Isaac Newton was developing his sort of description of motion, there was another researcher named Hamilton who was doing something very similar. And that has nothing to do with the first treasurer. I forget Hamilton's first name. Hamilton had was describing motion with two quantities. He didn't know what they were, so he just called them P and Q.
Oh.
Turns out his quantity P is our quantity momentum. So even though we name, it seems like every damn thing after Newton, here's a little bit of a hat tip, like, hey there, Hamilton, I see you.
So what's the Q?
Energy, actually.
What's energy?
If Hamilton's P was momentum, what was his Q? Energy. The units for this should be kilogram meters per second.
For momentum.
Yep, because it's a mass in kilograms times the velocity in meters per second. And this thing, this equal sign right here, it's called the impulse momentum theorem. This is what I just said was impulse. This is what I just said was momentum. So this together, this relationship is the impulse momentum theorem, just like we had the work energy theorem. So what does that equal sign mean? If we ask not for the force, but for the net force applied over time, that's the net impulse. All the forces acting applied over time, add it all up as vectors, that's the net impulse. And this equal sign says that that's equal to the change in P.
So that's the impulse theorem?
Yep.
Oh,
Yeah, it's just this again, written with the new definitions. Here's impulse. Here's momentum.
right.
Yeah.
So impulse equals momentum?
Net impulse equals change in momentum.
Okay.
Just like,
Oh, EJ, oh. What am I doing?
just like net work is equal to change in kinetic energy. So in each case, we take the force and add it up. And that means a change in a motion. Here we got the same thing. Take the net force and add it up. That's the change in the motion. In fact, when Newton originally published his second law of motion, he wrote it this way, as momentum.
So what made it change? Was that wrong?
No, but that's still right.
So why did it change it?
We didn't, or he didn't.
We didn't.
The intervening 400 years of people writing textbooks.
Oh,
Eventually, someone along the way decided that it made sense to present acceleration first. I have seen textbooks that start from here, which I think is pretty cool. And they'll only then go back and talk about acceleration,
Backwards,
kind of.
way of teaching. Huh.
But that makes sense, though, if you can get things, you do a lot of things.
All right. Technically, yeah, it's the impulse momentum theorem, but it's really just Newton's second law. Like all we did was cross multiply and then redefine some shit. In other semesters, I have skipped energy and gone right from Newton's laws to momentum
Why?
because it's right, we're here and we don't need anything new to rearrange it and then just say, oh, look at this new thing, I'm going to call it momentum. Like it's right there in Newton's second law. I also think it worked the way we just did it, going from Newton's laws to work and energy and then to momentum. I think we can tell, make a good narrative string from topic to topic either way. I'm not sure which I like better. I'm curious which you might like better, but that's going to be hard to determine because you've seen it one way now. And I'm not going to go back and teach it again.
Now learning backwards.
Yikes. Now, what does any of this have to do with reconstructing a car accident?
Oh, momentum. Oh, direction. Where the car was.
You can tell what started it. No, okay, so we have where the cars are, right, which is based off the momentum. So once we go backwards, we can say what started it, right, from the impulse there.
Yeah, pretty much. We need to say something about the collision itself. And we do have directions before and after, right? We know that the car skids 33 degrees north of west. We know that the truck skids 7 degrees north of west. And that makes me think about vectors. Right? So I can tell the momentum story before and after the collision. I just need to figure out a way to connect the two. Have any of you fired a gun?
Yes.
Was there any kickback?
Oh, yeah, I actually jammed the gun because I got scared, like, yeah, I fucked it up. Yeah, there's a lot of kickbacks, especially if you're not holding it.
There's kickback because of Newton's third law. If the expanding gases in the combustion chamber push on the bullet, then that bullet also pushes back on them, which pushes back on the gun, which pushes it back into your shoulder. So all together, what's the net force? I throw the backpack. What's going to happen to me?
Oh, you're gonna be projected back.
Push backwards. Just like the gun recoiling.
Yeah.
right now, what is the net force acting on me holding my backpack?
Oh, here.
0. Right? Gravity pulling down, the normal force pushing up, nothing's happening. Does me throwing it change that story at all?
Why you want to?
We're going 2 different directions. And yeah, if we talk about the backpack only, I'm applying a force on it, and that's why it's accelerating. And if we talk about me only, well, it's pushing back on me, so I go back that way.
But the gravity and the normal force are
The
still-
gravity and the normal force are still the same. So if we talk about the backpack and me as some sort of weird composite object, what forces are coming from outside to push on us together?
Gravity.
Gravity and the normal force. While I have the backpack in my hands, while I'm pushing it, it's still being held vertically by the whole situation here. Once I let go, I'm not applying a force anymore, and it isn't applying a force on me. But during the time that I'm throwing it, it's pushing me back. And that whole time, the net force on the 2 of us is 0. We throw the backpack. After having been thrown, it has some momentum
Which is forward.
What,
that way.
Okay.
what were you saying by the net force 0? Sorry. The instant that it's thrown? Or the
Which the whole time there's gravity and normal, and they cancel out. So if you consider the pair of us together,
Mhm.
there aren't any forces coming from outside to push on us together. No net force anyway.
Oh, okay.
We're going to push on each other, sure,
Mhm.
but nothing comes from outside to push on the pair of us as a unit, because gravity and normal force cancel each other out. I push the backpack, it goes that way, some momentum that way. The recoil pushes me this way, some momentum this way. I've got momentum this way. The backpack has momentum that way. How much altogether momentum are we going to have?
Between you and the backpack.
All together.
0.
0,
Because y'all have
positive and
both.
negative.
How much net force was there on me and the backpack?
0.
0. Do that for some amount of time.
Still 0.
Change in momentum overall for the two object unit, 0.
So what did that do?
0, you're right. Total momentum before is 0, because I was just sitting with the backpack. Total momentum of the system, that weird composite object,
Oh,
still
okay.
0.
You-
Some of it's going this way, some of it's going that way, in equal momentum, but opposite direction. So it's going to add to 0, and in fact, it has to. The net force on the composite object is 0. So the momentum of the system cannot have changed. Within a system, I can push on something else and it pushes back on me. This is the problem. I can't lift myself by my own shirt because I can't apply an external force on myself. I can't push on me. I can push on the backpack, but that doesn't only push on the backpack. If there were less friction, the backpack might stay put and I might go.
So is that kind of what the collision is?
We've got a Newton's third law problem during the collision between the two vehicles. But if that is internal, to the system of the two vehicles, then the fact that one exerts a force on the other, who cares?
Yeah.
As long as the net external force is zero, then the total momentum of the system has to be what it was. So however much north going momentum you have, and however much west going momentum you have, sure, there's a collision, but if the collision is short compared to the rest of the story, yeah, the collision only lasts a fraction of a second, right? They stay in contact only for a fraction of a second.
So it has it has like constant momentum, but it never stops because it's,
Right. Whatever momentum we had, sure, there's a collision, and those pieces of the system, like me and the backpack, exert forces on each other, like the gun in my shoulder, right? We push on each other. But from outside, we collide, and the only thing I can think of that would act from outside is friction. But if the collision happens with the vehicles kind of instantaneously at rest, or at least at rest during the collision, the like fraction of a second that they actually spend touching each other, then there's no distance over which friction does any work. There isn't any force from outside to change the momentum of the system. So however much north going momentum the car had, however much west going momentum the truck had, they collide, sure, shit scrambles, but when we're done, we need to have altogether as much north going momentum as we started with, and as much west going momentum as we started with. We've rearranged that momentum, shared it between the two cars, sure, because each of them is going a little bit west and a little bit north now. But if we put this in component land, we've got a north story to tell and a west story to tell, and the momentum in each story is constant across the collision.
so we're not involving the force of the engine at all? So does everything equal zero? I don't,
It doesn't in the case of the accident. For me in the backpack, it was zero because we were at rest originally,
But since
right?
they were.
But if I was already sliding and maybe I wanted to slow down, then I could throw the backpack and I could decrease my own motion by adding some to the backpack. That's sort of what happens here. Because the car and the truck are already moving, we start with some non-zero momentum. What has to be zero
That,
is the change in that momentum. Whatever we had to begin with, we have to have when we're done.
oh, wait, is the third law that energy gets restored?
The third law has to do with the equal and opposite forces between the interacting two objects. So the car crunches the truck just as much as the truck crunches the car. But that's all inside the system. I don't need, if I define my system of interest as the truck and the car together, then no one comes to push on that system from outside. So whatever it was doing, it should still be doing altogether. We might be able to rearrange the momentum within the system. But if we talk about the overall momentum of all the mass moving towards the intersection, exactly that much momentum has to leave the intersection in some way, because nothing exists to have changed it.
this first question has friction involved.
Yes, that's true. Because we need to know what's the story during the skid? We're gonna work backwards through this problem. We end having skidded so and so far. So what were the initial speeds? It's like the backwards of the stopping distance problem. Now we're told how far we go and what the friction was. So we need to unpack and say what the initial speed was right when they started to skid after having collided. But that moment, right after having collided, they have velocities in the skid directions. Those velocities have components. And they have momentum in north and west, each of them, according to the direction that they skidded after the collision. So if the total momentum story has to be the same before and after the collision, now we know how fast they were each going. Must have been going prior to the collision. And then hopefully we can decide who maybe did or didn't stop at their red light. The first two questions, we don't need momentum to answer. The third one we do. And I promise to present more information that will help you answer or sort of attack this scenario. But it's also 10 after 10 and we are all of us tired and
Yes.
ready to be done. So I will save this for Thursday. We'll talk about this demo on Thursday. And it should put things into a little bit sharper perspective for the accident reconstruction activity.
So wait, when there's an accident, do they actually just like bring a physicist and be like, what happened here? Like,
It is,
Really?
it is not uncommon. This is
That's really cool.
This is based on a true story in which a physicist was asked to testify in traffic court.
Seriously? That is so cool.
I think there was a story about a guy who proved that he wasn't speeding with the information from.
Yeah.
It was
No
really
way.
cool. And he presented all his information. to her.
That's amazing. He said if I was speeding, I would have gone 5 feet at least instead of 10.